welcome to topic 9, energy and work. So we are starting our energy section of physics in science 10. So here we go. Before we get started, let's review what types of energy we have talked about or you have heard. Take a second and jot down all of the important energy terms that you have talked about in the past. I will give you time to do that now. Press pause. All right, welcome back. Okay, what types of energy are there? Again, you may have listed some of these, all of these, none of these. Depends how dedicated you were to that. Different types of energy. There's mechanical energy, which we'll get to later in physics. Thermal energy and chemical energy are big ones we've talked about already with obviously being in the chemistry unit. Chemical energy is stored in chemical bonds, right? When we look at something like methane, CH4, we know methane is something we can burn. Okay, so we can use a lot of these compounds to break those chemical bonds and release a ton of energy for very useful things. Methane is used in natural gas, which heats our homes. So a very, very positive use for that. We know thermal energy is heat. We moves from hot objects to cold objects. We talked about that a little bit in climate as well. But thermal energy is constantly moving. It's cycled in our atmosphere. It's cycled in our oceans. And we, again, chemical energy and thermal energy, we can transfer from one to the other. The big ones we look at in Science 10, particularly in this next little bit, is kinetic energy and potential energy. Kinetic energy is related to movement. Okay, whereas potential energy is stored energy. Okay, there are many different types of potential energy. Chemical energy is a type of potential energy because it's energy stored in bonds. Gravitational energy is a form of potential energy because it's energy stored as a result of position. So in Science 10, related to potential energy, we are focusing mainly around gravitational potential energy. But what we know from these types of energy is that energy can be transferred from one form to the other to do some pretty cool stuff. So the first law of thermodynamics kind of helps us understand that energy cannot be created or destroyed. It needs to be transferred into something else. So when we look at energy conversions, we can think of a ball rolling down a hill. Initially, the ball is going to have some energy related to its position above ground level, right? So we have it being at a certain height. It's going to have a certain amount of gravitational potential energy based on how high it is. The higher up it is, the more energy it can potentially do. Okay, or it can potentially release. Now, if we push this ball over the hill, we're going to see the ball pick up speed and roll down that hill. Okay, at the bottom of the hill, we're going to see kinetic energy. Again, the higher the ball rolled down the hill, the more kinetic energy it's going to carry at the bottom of the hill. But what we saw is potential energy get turned into kinetic energy by a simple push. Okay, and that's what we look at today is how that transfer can happen when we input a little bit of energy. So energy. Once an object has energy, that energy can be transferred into different forms. This energy can be used to complete a task, moving faster, turning a turbine, or climbing a hill. Okay, this sounds like a lot of work. Okay, work. So when we talk about this, okay, when we talk about work, work is just defined as some kind of change in energy. Okay, so energy is defined as the ability to do work and to complete a task. So we need some background information before we jump into this. So Newton's first law of motion says an object at rest stays at rest, and an object in motion stays in motion with the same speed unless something acts upon it to unbalance the forces. Okay, so in essence, in simpler terms, an object's going to keep doing what it's doing until something acts on it to change it. Okay, whether it's staying at rest or an object in motion with no acceleration, they're going to keep doing what they're doing unless something acts upon it to stop it. Okay? So the example here is a good old-fashioned game of tug-of-war. I'm not sure if you kids play this these days, but if we have 3 people on each side, okay, we can see in the first example way up here, okay, we have a pretty equal we have an equal force distribution. We have 300 newtons of energy or newtons of force being pushed to the right. We have 300 newtons of force getting pushed to the left. okay, the magnitude of that force is going to be equal here. Okay, so there's not going to be anything happening here. They're going to be at a stalemate. Okay, the center of that is going to remain constant until there's a greater force applied in one of the directions. Whereas if you look in the second example, okay, when you look in the second example, now we have less people on the right side, poor person on the right side, okay, only able to apply 100 newtons of force, so we see less force being applied to the right and the same amount of force being applied to the left. So which way, who's going to win this match? Again, the group on the left is going to win because they're applying a greater force. They're causing the person on the right to accelerate forward. Okay, so again, we're going to see the center of this remain completely the same because the forces are balanced in the first example. For this to be continued again, or second, when we talk about second law, this should be second, I think. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force. Okay, so we'd have acceleration is equal to the force divided by the mass of that object. Okay, as the definition says. Okay, so when we talk about the mass of an object, again, that's usually measured in kilograms. Okay, when we look at this second law, the forces are going to be unbalanced in this case, like that second example that we just looked at. When the forces are unbalanced, it causes an acceleration to take place. Okay, the acceleration depends on the net force being applied as well as the object's mass. Okay, so again, the greater acceleration, you're going to have greater force and less mass. Okay, so that's kind of what this relationship is telling us. Now, if we rearrange this, we can use this and look at force. Okay, force is equal to a push or a pull, energy applied to an object. Force is equal to mass times acceleration. This is just a rearranged form from the second law we saw in the previous slide. Mass is in kilograms, acceleration is in meters per second squared. The kilogram unit is probably pretty new. Masses from before have been in grams so far, but when dealing with forces, kilograms is what you're looking at. Now, with force, we usually represent them in newtons, okay, or an uppercase N or capital N. Based on the formula up here, we have the mass unit. 1 newton is equal to kilograms times the meters per second squared of acceleration. If you want to simplify this a little bit, 1 newton is equal to kilograms times meters per second squared, which matches the variables we see up in our formula up at the top. Okay, forces are vectors since they depend on acceleration. What does that mean? Well, since they're vectors, forces are going to have directions just like before. So we need to keep in mind that forces have direction, which is important when we are trying to figure out how these forces are being applied. So Mr. Rainier wants to move a box of kittens. Okay, we need to figure out, when we think about energy, how do we figure this piece out? You might be thinking, hey, like you have this wonderful diagram. Yes, we're not moving a car, etc. But it could be a really big box of kittens. Who knows? So if we're thinking about moving a box of kittens, we have the kittens sitting there. Okay, again, the kittens are going to sit there due to forces being equal to where it's sitting on the ground. Oh, sorry, this shouldn't be an arrow. That's just the ground. So if I wanted to move the box of kittens and slide it across the ground, I would need to apply a certain amount of energy to transfer energy into this box of kittens to get it to move. I need to overcome the forces that are holding it there, according to Newton's second law. So what do I need to do? If I wanted to move the kittens to the right, what variables would it depend on? Well, according to Newton's second law, we need the mass of an object, would be really, really important, and the force applied. Okay, and what else would be important? Well, probably how long I'm going to push it or how far I'm going to push that object. So when we look at the amount of energy required, we know that mass is already factored into force. But if I wanted to figure out the energy required to move this box of kittens, I'd be looking at these two variables, okay, to figure out how much force I would need and how long I would need to push that object. So when we look at work, okay, work is in essence that exact function. Okay, force exerted on an object that causes it to move in the same direction. The formula we look at here is a result of the force applied to the object and how far the object was moved. Okay, work is, W is for work, in joules. Okay, this unit probably looks pretty familiar from before. Okay, joules is our common energy unit, like we talked about before, if you remember. Change in energy equals work being done. Okay, F is the force in newtons. Again, this would be a vector quantity. Okay, and D is the distance the object is moved in meters. Okay, so when we look at this, 1 joule is equal to newtons times meters. Okay, now how can we change that? If we wanted to rewrite joules, we know a newton is kilograms times meters per second squared times meters. So 1 joule is equal to 1 kilogram times meters squared per second squared. If you wanted to reinterpret that and kind of expand out the units a little bit more. Again, it's dependent on a whole bunch of things of distance, okay, acceleration, and mass. Okay, so that's our basic work formula. Now, work is only being done. There's some criteria that needs to be happening here. There must be movement taking place. Okay, there must be a force applied, and the direction of motion is in the same direction as the direction of the force being applied. So an example here, I'm holding a 2 kilogram block of cheese. So I'm going to draw my block of cheese as this little square here in my hands. Okay, so I would be assuming that here's my arms. Okay, there's my hand there. Look at that, that's beautiful. Okay, that's beautiful. Okay, so we have the arm holding the block of cheese. Okay, as I'm holding the block of cheese, okay, in my hands, I walk across the room. Okay, so we need to analyze what's happening here. So what am I applying? What force am I applying to the block of cheese? Well, I would be applying an upward force to hold the cheese in my arms. As I'm holding the cheese in my arms, I'm walking across the room. So the motion is going across the room, whereas the force is going upward. Do those match? Is the direction of the motion the same as the direction of the force being applied? No, they're opposite to each other. Therefore, if they are opposite, we know work is going to be equal to 0. As a result, they need to match each other. Direction of force needs to be equal to the direction of the motion. Okay, so the direction of the force is up against gravity, and the direction of motion is horizontal. So no, there's no work being done. Diagrams are really, really helpful to you analyzing what's happening in a question. It's a good habit to get into. You don't need to be an artist. You just need to be able to draw a box and represent things to help you figure out the direction and how forces are being applied. Another example, okay? A dog lifts a bone from the floor. Okay, if the dog exerts a force of 0.5 newtons over a distance of 0.2 meters, how much work is being done lifting the bone? So again, we're going to have the ground level, we have the dog bone, the bone is being lifted up in the air, so we have a force being applied upward, and we have motion of it moving 0.2 meters. So in this case, our direction of the force being applied and the direction we're moving is both up. They match. So work is being done. So we're going to plug in the work formula. Force, change in distance. What are we given in the question? We don't really know what work is. Our force here, force is in newtons. So I know that it is 0.5 newtons. And our change in distance is 0.2 meters. Again, use the units to help you identify what the variables are, and we can just plug in and solve. This would give us 0.10 joules is equal to our work value. So our change in energy, okay, would be a positive 0.10 joules of energy. Okay, hopefully that makes sense. So let's do another example. Okay, the engine of a car has a mass of 1,500 kilograms and suddenly stops working when traveling 20 kilometers an hour. Kilometers an hour tells us that this is a speed. Kilograms tells us that that is a mass. The car travels 160 meters before coming to a complete stop after 13 seconds. Again, another number helps us assign variables. Assuming the only force responsible from stopping the car is the friction between the car's tires and the road, find out how much work needs to be done by this force to bring the car to a complete stop. Okay, so apply what we know. So in this particular example, what are we given? We are given a mass of 1,500 kilograms. Okay, V1 is going to be our 20 kilometers an hour. Okay, our V2 is going to be 0 kilometers an hour. Our T is going to be 13 seconds. And what is the question wanting us to do? We are trying to find work. And yeah, we know work is equal to force times distance, so we're probably going to need a force here as well from the previous question. So how can we figure this out? So first of all, don't really like kilometers per hour usually. Let's convert that into a more manageable number. Okay, if I remember correctly, this should be 5.6 meters per second. Okay, so we can work backwards here and figure out force first. Okay, now why do we need force first? Well, we know work, is equal to force times the distance. Now we know what the distance the car is stopping in. We don't know work, we don't know force, so we have too many unknown variables. So we're going to start with force. We know force is equal to mass times acceleration, as we mentioned in Newton's second law. We can change this because we remember what acceleration is. So we can go mass times V2 minus V1 divided by our time value. In this case, we'd have our mass being 1,500 kilograms. It's in the right units, so that's nice. And we'd have V2, which is 0 minus our 5.6 meters per second divided by 13 seconds. We plug this into our calculator and we get negative 640.96 newtons for our force. Now, since we have our displacement in our question of 160 meters, now we can plug this in and take it a step further. So now we're going to use our work formula and go work is equal to force times the change in distance. We have our force of negative 640.96 newtons times our 160 meters. This would give us an answer of negative 1.0 times 10 to the 5 joules. Okay, if we're keeping our number of significant digits, etc., we'd have 640.96 times 160, which would give us, 102, since 3 significant digits. And we'd have the negative value since we're applying we're again changing energy in the negative direction, which makes sense with the slowing down component since we have a negative acceleration as well. So hopefully that made a little sense of how we can tie those two formulas together to find some unknown variables. Just using the formula above, we can calculate an average amount of work over a distance, assuming a constant force. However, this is not always the case. So again, we have to make some assumptions to make those use those previous equations. On the graph of a force versus position time, or a force versus position graph, the area is equal to force times the change in distance. So the area under the graph here would be equal to work. Okay, this goes back to finding the exact things of before. Area of a triangle, an area of a rectangle. We're going to keep it to those shapes for the most part. But again, if we looked at a shovel pushing more snow, more force is required as snow builds up in front of it. So we see an increase in force as the distance of the snow shovel travels. Okay, so we see a line of a force and distance. We know force is on the y, distance is on the x. So the area under, if we're multiplying, is going to be equal to the work being done. So we're just finding the area under the line as we did before. Okay, so we can kind of work through this. We break this into two simpler shapes like the diagram is showing us. We'd have A1, which is a triangle, which would have 1/2 base times height. We'd figure out what the width of it is, and we'd figure out what the height is by subtracting the two. of subtracting 80 minus our minus 50, which would give us 30. We multiply those together, divide by 2 to give us 375. The area of section 2 would just be the rectangle. 25 times 30 gives us 750 joules. The total area would be added together. That would be our total work if we had a force distance graph, just like we did before with some VT graphing and displacement. If we have again a nonlinear one, just as before, we'd find the amount of work per one square of the graph, and we count the number of squares under the graph. If half or more is counted or covered, we count it as 1, 0 for everything else. We multiply the amount of work per square times the number of squares if it's non-linear, right? So this is in the situation where we have a force change in distance graph of something that is curved. Okay, just like before, that's how we approximate the area underneath it to find that work being done. Okay, so take a few seconds. Hopefully you can write down 4 or 5 key points from the video, bring them to class tomorrow. Hopefully it makes a little bit of sense with what work is and how energy is important with that. And if you have questions, write those down as well. Again, we want to focus on not only taking as much as you can from the video, but I want this video to generate some questions from you. So hopefully we can use that in class to continue the learning with the examples. That's all for now. Thanks. Bye.